In fact, order of growth classifications are so important, they've led to an enormous amount of research in recent years, and we'll just talk briefly about that now. Life is a little bit more complicated than pointed out in the last example. And one problem is that the inputs can cause the performance of the algorithm to vary widely. So often we have to think about different ways of analyzing the algorithm depending on the input. So the running time is going to be somewhere between the best case and the worst case. Best case is a lower bound on costs. It provides something that the running time is going to be bigger than that always, or not less than that. And then there's the worst case, which is the most difficult input. If we analyze that, then we can guarantee that the running time of the algorithm's not going to be bigger than that. And then in a lot of situations, we might consider our input to be random. Well, we need some way to model what we mean by random for the problem that we're solving. But there's a lot of situations where we can do that, and then we have a way to predict performance, even when the input might vary widely. So, for example, for three-sum, it's kind of always the same. With the tilde notation, the only variability in that algorithm is the number of times the counter is incremented, and that's in low-order terms, so it doesn't even show up in our analysis. For binary search, you might find the thing right away, in which case it's constant time, and we can show that the average in the worst case are both log base 2 of n. And there's in other examples there'd be much more variability even. We have these different types of analyses depending on the input, but the question is, what about the actual problem that the client's trying to solve? So we have to understand that too in order to be able to understand performance of the algorithm. And there's two approaches that are successll in this. One is to design for the worst case. Just make sure your algorithm always runs quickly, and that's definitely ideal. Another is to, if you can't do that, is to randomize and then depend on some kind of probabilistic guarantee. We'll see examples of both of these as we go through the course. Now, those kinds of considerations and the idea of order of growth leads to a discussion of what I call the theory of algorithms. And here our goals are, we have a problem to solve, like solve the three-sum problem, and we want to know how difficult it is. We want to find the best algorithm for solving that problem. Now, the approach that computer scientists use for this is to try to suppress as many details as possible in the analysis. And so just analyze the running time to within a constant factor. That's what order of growth is getting at. And also, we want to not worry about the input model at all. And so we focus on worst case design. Then we can talk about performance of algorithms just in terms of the order of growth. And it's actually possible to do that in a very rigorous way that has taught us a lot about the difficulty of solving problems. And our goal is to find an optimal algorithm where we can guarantee to within a constant factor certain performance for any input, because we discovered worst case. But we also can have a proof that no algorithm can provide a better performance guarantee. I'll give a couple of easy examples of this. Now, in order to do this, there are these commonly used notations called the big theta, big O, and big omega notations. And those definitions are given here. So the big theta notation is just a way to describe the order of growth. Theta of n squared is kind of shorthand for anything times n squared. It's bounded above and below by constant times n squared. And that's what we really use to classify algorithms. And then there's big O notation, which is upper bounds on performance. When we say big O of n squared, we mean that it's less than some constant times n squared as n grows. And big omega is used for lower bounds, which means it's greater than some constant times n squared as n grows. So those three notations we're able to use to classify algorithms, and I'll show in the following. So the examples are from our one-sum, two-sum, and three-sum are easy to articulate. So our goals are to establish the difficulty of the problem and develop an optimal algorithm. So the one-sum problem, is there a zero in the array? Well, an upper bound on the difficulty of the problem is some specific algorithm. So, for example, the brute force algorithm that looks at every array entry is a specific algorithm. And it means that, and that takes O of n time. You have to look at it's less than a constant times n for some constant. So the running time of the optimal algorithm has to be O of n. That is, that specific algorithm provides an upper bound on the running time of the optimal algorithm. But in this case, it's also easy to develop a lower bound. That's a proof that no algorithm can do better. Well, for one sum, you have to examine all entries in the array. If you miss one, then that one might be zero. So that means that the optimal algorithm has to have a running time at least some constant times n, or we say the running time is omega of n. Now in this case, the upper bound and the lower bound match. So to within a constant factor, so that's a proof that the brute force algorithm for one sum is optimal. Its running time is theta of n. It's both omega n and O of n. That's, for that simple problem, it was okay to get the optimal algorithm. For more complicated problems, it's going to be more difficult to get upper bounds and lower bounds, and particularly upper bounds and lower bounds that match. For example, let's look at three-sum. So upper bound for three-sum, say our first brute force algorithm said that the proof was a proof that the running time of the optimal algorithm is O of n cubed. But we found a better improved algorithm whose running time is O of n squared log n. So that's a better upper bound. Lower bound, well, we have to examine all entries because, again, we might miss one that makes three-sum equals zero. And that's a proof that the running time of the optimal algorithm is omega of n. But nobody knows a higher or lower bound for three-sum. So there's a gap between the upper bound and the lower bound in open problems. Is there an optimal algorithm for three-sum? We don't know what it is. We don't even know if there's a algorithm whose running time is less than O of n squared, or we don't know a higher or lower bound than linear. So that's an example of an open problem in the theory of algorithms. We don't know how difficult it is to solve the three-sum problem. Now, this point of view has been extremely successful in recent decades. We have a new problem, develop some algorithm, prove some lower bound. If there's a gap, we look for a new algorithm that will lower the upper bound, or we try to find a way to raise the lower bound. Usually it's very difficult to prove non-trivial lower bounds. Trivial lower bound, like look at every input item, is not so hard. Non-trivial lower bounds, like for example, the proof that we talked about for the union find problem, are much more difficult. And in the last several decades, people have learned about the computational difficulty of problems by examining steadily decreasing upper bounds. So algorithms with better worst case running times for lots and lots of important problems. And plenty of optimal algorithms, and plenty of gaps still remain. It's a fascinating field of research that many people are engaged in. Now, there's a couple of caveats on this in the context of this course. And the first one is maybe it's overly pessimistic to be focusing on the worst case. We've got data out there, we've got problems to solve, maybe it's not worst case data. In lots of fields of engineering and science, we don't focus on the worst case. The worst case for this course would be for lightning to strike and it would be over. So we don't plan for that. And similar is true for algorithms. Maybe we should be focusing on understanding properties of the input and finding algorithms that are efficient for that input. And the other thing is, in order to really predict performance and compare algorithms, we need to do a closer analysis than to within a constant factor. We talked about the tilde notation in the big theta, big O, and big omega that are used in the theory of algorithms. And really, there's so much published research in the theory of algorithms that a lot of people make the mistake of interpreting the big O results that are supposed to give improved upper bounds on the difficulty of the problem as approximate models for the running time, and that's really a mistake. So in this course, we're going to focus on approximate models by making sure that we use the tilde notation. And we'll try to give specific results for certain quantities of interest, and the constant, any unspecified constant in the running time will have to do with properties of the machine and the system, so that we'll be able to use these results to predict performance and to compare algorithms.